Okay, good morning, everyone. Let's get started. So first of all, just a reminder, please start doing homework at 1. It does need some time to implement your decision tree and different calculation of the information gains. And also be aware that we need to submit your project selection and your team. I think after homework deadline, well, 2 days or 3 days, I kind of forgot. Please make a decision as soon as possible. So by the way, this is something Amsterdam still asked me to clarify, right? So as I made announcement on the canvas, if you're doing exploratory project, please also submit a very small project proposal, just explain to us like what kind of problem you want to do, why do you want to do that, why do you think machine learning will help, and that's it. And no more than 1 page. Right? Half a page will be ideal. And if you're unclear about what I'm talking about, please look at the course webpage. We actually have walked through the requirement very in detail in the first week, right? So don't forget to attach your project proposal if you're doing research project. If you're doing Kaggle or computation project, you don't need to write any project proposal because the problem is there, right? But you do need to create an account and make some dummy submissions to show us that, okay, you have already known how to submit your solutions and doing test. Any question? Okay, great. So let us continue with the computational learning theory. So in the last lecture, we introduced several basic concepts from a fundamental perspective to kind of measure or quantify how well a machine learning model performs, right? So we'll talk about the generalization error and the empirical error, right? The generalization error means that what is the probability for any instance which comes from the underlying data distribution, your learned hypothesis make a wrong prediction, right? So you can view like you're doing some kind of expectation across the whole instance in the instance space, right? So it is a constant value. It's not random variable. But because you don't know the data distribution in most of realistic cases, is very complicated. So you won't be able to calculate what is the probability the distribution density for your problem, right? So that means you are not able to calculate the real generalization error. Instead, people will seek for empirical error. So empirical error is actually the training error. You just use your learned hypothesis to make predictions on training set and say what is the fraction of your mistakes. This is called training error, right? And because the training error depends on the particular training set you used to calculate, right? And the training set, we know they are randomly drawn from the data distribution. So training set itself is random. So the training error or empirical error is a random variable. So this is very important. Please keep it in mind. Right? It's kind of like I want to reinforce this this concept to make sure like everybody is on the same page, right? So later we'll see like how do we use empirical error to bound the generalization error, because the empirical error itself is a random variable. So that bound is a probabilistic bound. It's not a deterministic bound. We'll see that in detail later. Right? And then we introduce the important concept called PAC learnability, right? It is abbreviated for probably approximately correctness learning, right? So basically, this is a pretty lengthy definition, but I want to emphasize the intuition here. So this actually proposes a criterion differentiating the efficiency of different learning algorithms. Right? So if a learning algorithm is efficient, meaning that it could use not too many training examples to arrive at arbitrary accuracy on the arbitrary data distribution with arbitrary high confidence. Right? That's the idea of the PAC learnability. So if we want to look at this definition again, right, we say if our machine learning model L can pack learn some type of target function, which is denoted by concept class C, if for every possible concept or target function in C, for every possible data distribution, and for every setting of the error level epsilon, and every level of the probability confidence, right? And the number of training examples required to arrive at this given error level and under this given high chance 1 minus delta, the number of training examples is only needs to polynomial in 1 over epsilon, 1 over delta, the number of training, number of features, and size of hypothesis space. Right? So this length is just means like, okay, when you kind of like make a stronger requirement of the performance of your learned hypothesis, your required number of training examples doesn't grow like exponentially. It just grows polynomially. It's not crazy. So if your algorithm can do this, right, then your algorithm will good, and it's so-called pack learnable, right? And and we can also add one more requirement that, okay, we call this concept class C is efficiently pack learnable by L if the finding or learning procedure itself, the time complexity is also polynomial in these 4 numbers, right? That means, okay, not only would your learning algorithm require like mild growth of training examples, but also the computation complexity is mildly growing according to your specific setting of epsilon, delta, n, and hypothesis space size. Does it make sense? Right? So that's the key idea of pack learnability. And someone asked, okay, is this the only criterion for us to, differentiate efficient learning models and inefficient learning models? The answer is no. You can define your own criterion. You can propose another, say Bob's learnability, whatever, right? And you can also use that to classify efficient learning algorithm, inefficient learning algorithm. It's up to you, right? Here we just give a definition which is widely used and popular and widely accepted in the theoretical community. Okay. So for pack learnability itself, we actually impose 2 requirements. First is about sample complexity. I mean, so sample complexity must be polynomial, not be exponential or even higher than exponential. Then we will okay, our learning is efficient. So that basically means, okay, when we want to increase the performance or increase the accuracy of your learned hypothesis, we do need more data information, right? However, if you just need a polynomial growth of the data points, that means your algorithm is quite efficient in leveraging those information, or absorbing more and more information to find out better hypothesis, right? But on the contrary, if you need like exponentially growing sample complexity, that means your learning algorithm is not that efficient in leveraging the data information. Okay. And another is polynomial time complexity, which is reasonable, right? You want your learning procedure itself is efficient enough. You don't need to run an algorithm forever and ever. And also pack learnability is a worst case definition. You see that is very strong assumption. We want an algorithm to meet its accuracy for every possible distribution and for every target function in the concept class C, right? So you can visualize as a bottom line definition, right? Of course, you can propose other definition. Okay, any question regarding the understanding of pack learnability? Okay, perfect. Okay, now we want to use the very simple, concise framework we have built up to justify this Occam's razor principle, right? remember, what is Occam's razor's principle? We talk about ID3 algorithm for decision tree learning, right? And what is Occam's razor? Yes, yes, exactly, right? We mentioned that, okay, suppose you're given a set of different models which can equally explain the same data, right? And then which one should I use? I should choose the simpler model, right? The simpler, the better, right? This is called Occam's razor's principle, right? We mentioned that, okay, this is kind of widely used in scientific engineering domain, but do we have some mathematical justification, right? We just don't want to like talk everything. It's just, okay, this is our theory, this is our bias towards the model selection, right? So at least we should provide some rigorous justification for this, right? And explain why should we do this, right? So now we're going to use our computational learning framework, which is very rough and framework, but it is sufficient for us to justify the benefit of using Occam's razor's principle. Okay. So, but to summarize, Occam's razor's principle basically says it prefers we should prefer simpler explanations over more complex ones, right? And historically, this is like a widely prevalent idea across different schools of philosophy, and it comes from the philosophy. Okay, so now let us try to make efforts toward formalizing Occam's razor's principle, right? So here we want to use what we have reviewed in homework 0 to show this claim, right? Remember homework 0, we kind of like systematically review several basic concepts about random variables, expectation, probability inequalities, right? Hopefully you will feel they're really useful here. Right? Okay, so this is a claim we want to show. We claim that the probability there is a hypothesis in some hypothesis space such that the generalization error of this H is bigger than epsilon, but the training error is 0. So here, the second item just means the training error is 0. It means like, okay, H is consistent with all M training examples. So this probability can be bounded by the size of hypothesis space times 1 minus epsilon to the power of M. M here is the number of training examples. Right? So here our basic assumption is that, okay, your hypothesis is good enough so that it can well fit the training data. The training error is 0, right? So one example is decision tree, right? I mentioned that decision tree, if you don't restrict its growth, it typically can arrive at 0 training error, right? But now, there could be some chance that you have a perfectly trained model, H here, it refers to H, right? And it has 0 training error, but its generalization error is relatively big. Here, by relatively big, I mean, okay, it is bigger than some epsilon. So this is some kind of like event which I'm not happy, right? So usually I would like, okay, now that I have 0 training error, I hope my generalization error will be very, very small as well, right? But let us consider it is possible that sometimes you got 0 training error, but your generalization error is still big, which is bigger than epsilon. Is it possible? Why is it possible? Not, let us just not talk about overfitting. Let us assume, okay, the training data is perfect, doesn't have any noises. But we still have 0 training error or 0 empirical error, but my generalization error is still relatively big. Is that possible? Why? Mm-hmm. Yeah, exactly, right. So here, the K inside here is that your data is random, right? the training data is randomly drawn from data distribution, right? We mentioned before. If this time your training data is good, right? It's a good example from the whole instance space. It covers the whole instance space beautifully. Well, you can imagine, okay, your learned hypothesis will generalize well, right? But what if you have some chance you draw a training data set which is not representative enough, right? Even you have a zero training error, your generalization errors can still be bad, right? It is possible, right? So you don't, although this chance could be low, right? But that doesn't mean like there's no chance, right? There's still some chances that, okay, you have, you draw a set of training examples, which is of bad quality, right? And although even you have a very powerful training algorithm, you perfect fit to the training data, because of the limitation of the training data, you can still not get a perfect generalization error, right? So this claim is trying to bound the probability of such bad events occur. Right? So now let us read through this again, right? So want to claim that the chance that there exists a hypothesis such that it has zero training error, but the generalization error is still bigger than epsilon. This chance will be bounded by the size of the hypothesis space times 1 minus epsilon to the power of m. Here m means the size of the training data. Does it make sense? Right? So I would emphasize again, right? The randomness comes from the training examples. And h itself, like give any small h, right? You know you will definitely know it has some kind of generalization error. It is deterministic. However, because the random sampling of the training data, and it kind of like influence the learning procedure and end up with finding different H, right? So that means, okay, you might end up with different selection of H with different generalization error. That's why we still have some chance that you got bad hypotheses which have relative larger generalization error. Okay, so then let us try to show this, right? How can we quantify our chance to find such a bad hypothesis, even though it has zero training error? Okay, so let us assume that, okay, we are given a specific H, right? This H has already known, and it has generalization error bigger than epsilon, right? Let's say what is the probability this H is still perfectly fitting the training data. So we know that because the generalization error of H is bigger than epsilon, so for any instance drawn from the data distribution, the probability of H making mistakes in terms of prediction on X will be less than 1 minus epsilon, right? That comes from definition, right? The generalization error is the probability your H of X is not equal to F of X, right? If that one is bigger than epsilon, then the probability your H of X is equal to F of X will be less than 1 minus epsilon, right? So now, from the definition of the generalization error, we can get the first we can get our first conclusion that, okay, we have a particular hypothesis whose generalization is bigger than epsilon, but it can still correctly predict one training example. This probability will be less than 1 minus epsilon. Does everyone agree? Right? Is everyone comfortable? Okay. And then, because our training set consists of n examples, right? And here we're assuming those training sets are drawn independently, meaning every example is drawn IID from the data distribution. IID means identically and independently distributed, right? So that means, okay, the probability our H is consistent with all m examples will be less than what? 1 minus epsilon to the power of m, right? Does it make sense? Right? Because every training example is independent to each other, right? Then H, and we know H is consistent one example, this chance is less than 1 minus epsilon, right? And then H is consistent with every example will be less than 1 minus epsilon times 1 minus epsilon. You just time for my m times, right? Which gives this 1 minus epsilon to power of m. Any question? Everyone feels comfortable? Okay. Okay. So then we can conclude that H is bad, but still consistent with M training example. This probability, the chance of this event will be less than 1 minus epsilon to the power of M. Right? So now we have find out, okay, we from the definition of the generalization error, because the definition of generalization error itself is the probability you make a wrong prediction for any example, right? So you know that means if this probability make mistakes bigger than epsilon, the probability make a right prediction will be less than 1 minus epsilon. So you have M training examples, the probability you make correct prediction for all M examples will be less than 1 minus epsilon to M, right? And now we want to extend our conclusion, right? What's the probability that there exists some bad hypothesis which is still consistent with M training examples? You see the difference here, right? So this conclusion comes from, okay, I know H is bad. I know H is bad. By bad, it means that its generalization error is less than epsilon, right? But now I extend my statement to be, okay, existence statement, right? How would we quantify the probability that there exists such a bad hypothesis who is still have zero training error? So how do we get to this probability? So let us try to look at, if we look at this, there exists some hypothesis, some bad hypothesis, which is consistent with all M training examples. We can view it as an event, right? If we look at the event, right, we can denote this event by A, right? Our event A means that, okay, there exists some bad hypothesis in our hypothesis space, yet it is consistent with all M training examples, right? So this event actually is telling us that it is either the first hypothesis in hypothesis space is bad, yet consistent with all M examples, or the second hypothesis, H2, is bad, yet consistent with all M training examples, or the third is bad, yet consistent with M training examples, or blah, blah, blah. The last hypothesis is bad, yet consistent with M training examples, right? You can see that it actually is a union of a set of sub-events, right? Does it make sense? Okay. So we can write our event A as a union of a set of individual events, right? B1, B2 to B size of H, right? Each sub-event indicates for a particular hypothesis in a hypothesis space who is bad, yet is consistent with all training examples, right? And then leveraging our probability inequality, right? We know that the probability of a union of a set of events will be less than or equal to the summation of the probability of each individual event, right? Does it make sense? Right, this is our, I don't know, maybe problem 2 in homework 0, right? And what's the bound for each individual probability? Remember, the individual probability states that, okay, for a particular hypothesis, who is bad, yet has zero training error, right? We have already got this bound in our last step, right? In our previous step, which is upper bound with 1 minus epsilon to the power m, right? So now you add all those bounds together for every individual events, which means that you can multiply this bound by the size of hypothesis space, right? So now we get our bound, right? We get our bound that is the probability that there exists some bad hypothesis which yet is consistent with all M training examples. This probability will be upper bounded by size of hypothesis space H times 1 minus epsilon to M. Does it make sense? Okay. So now let's see from this bound, what kind of insight can we get? Okay. So we have proved that the probability of existing a hypothesis in the hypothesis space, which has zero training error, yet the generalization error is still bigger than epsilon, is less than this upper bound, right? So there will be a natural question, right? Okay, this event is a bad event. I don't want to learn a hypothesis which seems perfect fit to the training data, yet the generalization error is big, right? I don't want that to happen, right? So I want to reduce the chance of that bad event to happen. And what should we do? I mean, intuitively, what can we do to reduce the chance that you learn a perfect hypothesis that fits the training data with 100% accuracy, but you have still large generalization error? Yeah, use more data, right? Use more data. Imagine that, okay, although your training set is still random variable, but because the size of data is so large, it has a very low chance to be just covering a very small corner of the whole instance space, right? It has a larger chance to better represent the comprehensive instance space, so I can expect my generalization error will have a high chance to be smaller, right? That's our intuition, right? Now I want to quantify our intuition, right? So suppose we want the probability of this bad event to happen, want to control this probability, want to control this probability to be smaller than some delta. Say I can set my delta to be 0.01, right? Then I will say, okay, at least how many training examples should we use? Right? So because the probability that you have a perfect learned hypothesis yet has larger generalization error is less than this bound, right? If I want the probability of this bad event happen to be less than some designated threshold delta, right? I can simply let the bound, that is upper bound, less than this delta, right? So that means if I want to control the probability of this bad event, I can try to control its upper bound. And I can make this upper bound less than my given threshold delta, right? And we see that this upper bound is decided by the hypothesis space H, right? It's decided by, of course, the epsilon level, and also decided by number of training examples, right? That kind of consistent with our intuition, right? If you want to make our delta to be small, you can imagine your M to be large, right? Because epsilon is small, right? It's 1 minus epsilon is less than 1, right? So you want to make it right-hand side to be small, you have to make your left-hand side to be small. And that means you need to make a power M here to be large, right? So now let us try to solve this inequality in terms of M and say what is the requirement of the number of training examples M, right? So first we can take logarithm on both sides, right? To simplify it. So on the logarithm, you got logarithm size of hypothesis space plus M times logarithm 1 minus epsilon less than logarithm delta, right? This is kind of like, first grade, not first grade, maybe 5th grade math, right? And then, and to further simplify the results, right? To further simplify the results, we're gonna leverage some expansion of e to the power minus x, right? It's still expansion of e to the power minus of x. Then from that, we can show that the logarithm of 1 minus epsilon will be less than minus epsilon, right? So I can further, so you can see that this term has upper bound minus epsilon, right? So I can further make the whole left-hand side upper bound by logarithm delta, right? So that means I want to make log size of h times m times minus epsilon less than logarithm delta. Then I just solve this inequality in terms of m, which I can get here, right? M epsilon is bigger than right hand side, and then I claim that I can find that if m is bigger than this guy, then the probability of getting a bad hypothesis with zero training error will be small than our given delta. Does it make sense? Okay. So this is actually called sample complexity bound. So the result we have derived so far is that, okay, if I want to know, if I want to control some training event, that event is not a good event. That event is, okay, I have zero training error, but my learned hypothesis, it still has a relatively bad generalization error. I want to control the probability of this event to be less than some threshold delta. Then how many training examples should I at least use? And from this relatively simple derivation procedure, we know that, okay, if I make my number of training examples bigger than this lower bound, then I guarantee that the chance of this bad training outcome will be less than delta. So if you still feel like a little bit uncomfortable or feel not able to catch, it doesn't matter, because the math on the line here is really simple, but I do need some time to digest those information. This is kind of like a little bit twisted, but the idea is really straightforward and intuitive. Right? Basically, okay, you don't want your learned hypothesis with zero training error, but with large generalization error, right? How can you do that? You have to increase the number of training data points, right? And then we want to know, okay, how many training examples do I need at least to have to avoid this chance to happen? Meaning to make this chance to happen to be less than some threshold, like 0.01 or 0.001, right? If that's the, and then through this derivation, we can derive the bound, the lower bound of the number of training examples we want to use. Right? This is also kind of sample complexity bound. Okay. So now let us inject our derived sample complexity bound into our statement and now rearrange them. We can make such a claim, right? If we can make our training set to be enough large, or in other words, if we can have enough number of training examples m, which is bigger than the right-hand side, then we can claim that we will find a hypothesis h with probability at least 1 minus delta, but the generalization error at most epsilon. And this hypothesis is consistent with the training set. Okay, let me repeat again, right? This is just the combination of the or restatement of the sample complexity bound we have derived, right? So if the number of training examples m is bigger than this lower bound, then our chance of finding a hypothesis with zero training error, but with true error bigger than epsilon, will be less than delta. That is equivalent to saying you have a high chance to find a hypothesis whose true error to be less than epsilon, right? So this is equivalent. Right? Does it make sense? Any question? You mean epsilon or delta? Hypothesis is hypothesis space. That means the range of the functions you want to search over. You want to find a hypothesis from that space H as your best approximation to the target function. This is hypothesis space, right? When we talk about supervised learning, any learning model should specify a hypothesis space, right? It's a search space. Yeah, like for example, you have your hypothesis space consists of all Boolean functions over 8 features, right? Then you have 2 to the power 8 possible Boolean functions in the hypothesis space, right? The logarithm of hypothesis space will be logarithm 2 to the power of 8, right? Right. It's just the count of number of hypotheses in a hypothesis space. Any final question? I mean, you still feel like a little bit uncomfortable with this statement. Never mind. I mean, don't worry. Just read through it for 10 times. You'll get it. But here, I just want to emphasize the K here. The K is I want to look at a quantitative metric, a quantitative way to guarantee that, okay, if I have sufficient amount of training examples, right, I can control the probability that you have 0 training error, but still have bad generalization error, this chance to be less than some given threshold. Okay, so now let us look at the structure of the sample complexity bound we have derived and see what we can discover, right? So the right-hand side here consists of 3 components, right? The first one is 1 over epsilon, right? So epsilon actually is the error, right? The generalization error level, right? Of course, you want smaller generalization error. You will need more training examples, right? You can see the right-hand side, right? The sample complexity bound of M is bigger than 1 over epsilon, right? So that means you decrease the epsilon. That means you require your learned hypothesis performs better. Right? Of course, you need more training examples, which is very intuitive, right? And the second thing is even more interesting, right? So you can see that the number of training examples required is proportional to the logarithm of the size of the hypothesis space. What does it reflect? It reflects that given the same epsilon, that means given the same expectation of the generalization error, given the same delta, I mean, given the same threshold, right? If I choose smaller hypothesis space, then the number of required training examples will be smaller, right? In other words, if you use more expressive, a larger hypothesis space, then the number of training examples of M required to achieve the same generalization error level with the same probability threshold will be bigger, right? Yeah, it reflects this, and also reflects our why should we bias towards simpler models, right? That's one benefit of following this Occam's razor principle is that we can reduce the number of training examples we want, right? And in practice, collecting training examples is not that easy. It's actually costly, right? If using simpler model can achieve the same epsilon and delta level, and then we should use simpler model because you don't need too many examples on that. That's how it reflects in the Occam's razor principle. Without necessity, don't increase the complexity of your model, right? And from the machine learning perspective, that means you have to add more training data. And adding more training data is not free lunch. Right? You have to either spend like more cost in devices or manual labor, right? So in many real world applications like nowadays in autonomous driving or in large language models, all kinds of stuff, like they kind of hire a large group of people help you labeling data, right? This is not free. Okay, the third one is straightforward, right? So if we want a higher confidence, meaning that I want to lower the threshold, lower the probability that you have some zero training error but still have bad hypothesis, you want to make this event, the chance of event happen to be smaller. That means you decrease the delta. You have to increase the number of training examples as well. Right? Right. So you can see that though our computational learning frameworks we have discussed so far is relatively straightforward. It's very easy, based on very basic concepts: empirical error, generalization error, and the probability statement about the performance of your learned hypothesis, right? With some probability, your learned hypothesis will achieve some certain level of the generalization error. But this framework has already delivered something useful, right? It delivers something that what's the minimum number of training examples would you need to achieve some generalization error level with some chance, right? And also this sample complexity bound reflects the benefit of the Occam's razor principle. Yes, if you use simpler model, right, you kind of reduce the number of required training examples. This is a kind of big advantage by following the Occam's razor principle. So now there's a natural question. So here we the bound we have derived so far contains logarithm of size of hypothesis space, right? That basically assumes that, okay, your hypothesis space is finite, like Boolean functions we just mentioned, right? But what if your hypothesis space is infinite? It's not uncommon in real world. Like consider you're doing neural network, right? And your weights are continuous for sure, right? So every weight of neural network is continuous. And that means like all possible different instances of your models are infinite, uncountable, right? So that basically means like your logarithm of size of h is not, doesn't have any reasonable meaning. And then this sample complexity doesn't hold anymore. Then the question is that, can we still find a reasonable sample complexity bound for such cases? Yeah, the answer is yes. Right? In that case, we need more delicate or more complex measurement about sample about the hypothesis space complexity. So here we use a very rough metric. That's just the count of hypotheses in hypothesis space, right? And that won't work if your hypothesis space contains infinite many hypotheses, right? And then we need to convert it into another representation. This representation is called VC dimension. So we will review this concept again and introduce the definition of VC dimension when we talk about support vector machines. Okay, any questions so far? Great. Now we're gonna switch back to concrete machine learning models and algorithms. So you can see that throughout our discussion, throughout the semester, our discussion will be kind of like interleaving between the concrete machine learning models and algorithm and some kind of like more theoretical fundamental insights about learning framework. We hope this kind of can stimulate our understanding in both sides, right? Okay, so next, in the next a few lectures, we're going to talk about a large set of machine learning model algorithms, which are very, very useful. This is called ensemble learning. So we'll mainly talk about two strategies. One is called boosting ensemble learning. The other is called bagging. Right? So both methods are incredibly simple. I mean, in terms of algorithm design and an idea, but they have like very solid theoretical foundations. There are many theoretical papers talking about their generalization, error bound, and so on. And in practice, they are also extremely widely used as very successful. So we're gonna start introducing boosting, and we're gonna introduce the most representative boosting algorithm, which is called AdaBoost, right? So which has already been used in many modern applications. And then we'll talk about bagging methods. You see that bagging method is even simpler. Okay, so first, what is boosting? So boosting is motivated by some theoretical questions. So was motivated by some discussion about theoretical computational scientists. So basically, it is a general learning approach to construct a strong learner from a collection of weak learners. Right? So so in 1989, Robert Shapiro, he wrote a paper. It's called Strengths of Weak Learnability. So it's kind of like asking, suppose you're given a collection of very weak learners, meaning that your classification accuracy might be just slightly below 50%. I mean, binary classification problem, right? Like maybe my classification accuracy is just slightly above 50%, maybe just the 55% accuracy, 60% accuracy, no more than 70% accuracy. Can we use some smart way to aggregate them together or assemble them together into a powerful learning algorithm which can arrive the prediction accuracy to be 95%? Okay. So this is a theoretical question. But when people start to address this question, like not only theoretically, but also practically, the boosting has developed a large family of learning algorithm. So, and turns out to be very powerful, right? So boosting is a class of learning algorithm that composes classifiers using other classifiers as building blocks. So in boosting, you can view like, okay, you have a set of your building blocks, a set of weak classifiers, and then you use a set of like use a smart way to assemble them into a much stronger classifier. So practical useful, like face detector, handwritten letter recognition, text classification. They all have like a popular boosting algorithm implementation. Like for example, the face detector, like it's very common in digital camera, or even use your iPhone to take picture. It will automatically bound faces, right, to help you adjust the angle, the position of your camera, right? So this is typically implemented by the so-called AdaBoost. Right? And handwritten letter recognition. So this is kind of like when you send mail in USPS, right? And USPS trying to dispatch the packages and dispatch the emails to different places and addresses, right? Right now, they're all forced to go through some automatic procedure, which is typically done by machine learning. And here, AdaBoost. And then for some like very hard to recognize letters, they will pick up and transmit it to human workers. Okay, so here we're going to talk about the formal problem setup for boosting. Right? So we previous time discussed pack learning algorithm, right? The algorithm which can pack learn some type of concept class, right? So we see if an algorithm can do this, right? This kind of algorithm is called a strong pack algorithm. That is, for any distribution over the instance space, for every possible error level epsilon, for every possible confidence level delta, right? This algorithm just needs a polynomial many random examples from the data distribution. You can the algorithm can find a hypothesis with high probability meaning at least 1 minus delta, to find and with generalization error less than or equal to epsilon, right? That's the pack learnability, right? And as we mentioned, this is kind of a very strong requirement. So now let us lower down the bar, right? Let us try to look at a set of like weak pack algorithm. By weak means that, okay, I'm not going to require like your algorithm can do this for every possible error level epsilon. Instead, I can set up a threshold gamma, right? I only require your algorithm can do this for epsilon bigger than or equal than half 0.1 gamma. And this gamma is usually taken to be very small, like 0.1, 0.2. And this type of algorithm, if it can achieve this, right, it's called weak pack algorithm. And practice people often call it weak learners. Then the question here is the formal question, or more theoretical question here is that, okay, does the weak learnability, which comes from this weak pack algorithms, can derive strong pack algorithm or strong pack learnability, right? Okay, people have made a serious efforts to make this answer to be yes, right? So here's just a brief history, right? So it was the question was proposed by Robert Shapiro in 1989, and then it proposed the first probable boosting algorithm called weak learner 3 times on 3 modified distribution and get slight boost in accuracy and apply recursively. This is the very original, very preliminary version. And then in 1990s, this another computational computer scientist proposed the optimal algorithm that boosts by majority. And in 1992, this is they are not limited their discussion in theory. They also do some experiments using boosting, but they found that their algorithm are not performing well in practice. And the real breakthrough was made in 1995. This year, Shapiro and Freund introduced this so-called ADA boosting algorithm, which we're going to introduce later, right? And they found that not only gives nice theoretical guarantees, but in practice it's worked really, really well. Right? And after that, a huge number of papers and practical applications were after ADA boost, right? And these two computer scientists won the Gödel Prize in 2003, which is kind of a top theoretical computer science award. Okay, so now we're gonna introduce ADA boost, right? That is the breakthrough made by Shapiro and Freund in 1995. It's actually also the most popular boosted learning framework nowadays, right? So we're gonna start with some intuition. Use some concrete example to illustrate the idea of ADA boost. Then we'll go to the algorithm framework. And finally, we'll briefly discuss why it works. Right? But there's still some kind of open questions in the behavior boosting algorithm. So you see that in boosting algorithm, you see overfitting in practical data. But interestingly, you won't see the overfitting causing bad things. Even your training data contains noises, inaccuracies, all kinds of stuff. Right? And you see that the training error goes down, the same goes to 0, but the test error won't jump up. Right? It's still testing either lasts or keep going down. So this is very interesting behavior of ADA boost. Okay, so to illustrate the idea of ADA boost, I want to use this toy example. So suppose I have this 10 examples in this plane. Inside this rectangle, they're either positive or negative. Right? Now I want to combine a set of weak learners to successfully differentiate or classify those positive examples and negative examples. Right? So by weak classifier, here we mean our classifier either is a horizontal line or vertical line. Right? There's no other angles, just either horizontal or vertical. Right? So the idea of boosting is as follows. So we're gonna set an importance weight to each training example. So at the beginning, every training example is treated equally important, meaning that their importance weight is the same, is 1 over the number of training examples, right? And then I'm gonna train my weight classifier on this equally weighted training set, right? So suppose I find my best classifier on this data, which is H1, and H1 is actually a vertical classifier, vertical line here, and this is a boundary, right? Clearly, because this is a weight classifier, you can't expect 100% accuracy in training set, right? So your classifier, even when it is applied in a training set, it makes 3 mistakes, right? So my error under those equally weighted training set is 0.3. Everyone agrees with this, right? You have 3 training examples, and you have 3 mistakes, and you have 10 training examples. So your error is 0.3. Okay. So the next step is the called weight adjustment, right? So for the next round, we're gonna increase the importance weight for examples that is incorrectly classified by H1. So you can see that H1 has made 3 mistakes, right? So to avoid next time it's gonna be mistakenly classified again, I'm gonna increase the importance weight for these 3 classifiers, three examples. And meanwhile, I'm gonna downweight those examples that has already been correctly classified by H1. So that's the key idea. So every time I look at which examples I'm doing wrong, I'm gonna increase its importance weight. And for those examples I'm already doing correctly, meaning I'm doing fine, I'm doing perfect on that, I'm gonna decrease their importance. Okay. So in general, we can use DT to denote the set of weights at round T for those training examples. We have a weight for each example, which indicates how much should the weight learner care about this example in its choice of classifier, right? And here we require that the summation of all the importance weights to be 1, right? So it's normalized. So now under this weighted or reweighted training set, right? I run my weight learner again. I got my best weight classifier, which we denote as H2. So how many mistakes does H2 make on the training set? It's still 3, right? Those circle ones. But now the error is not 0.3. It goes down to 0.21. Why? Yeah, because we have to count the weights, right? Because those 3 examples, 3 negative examples, are correctly classified by H1. So their importance weights is reduced. So that's why when we calculate the error, we're going to add up their weights together. So their total weights will be less than 0.3. It is 0.21. Right? Okay, this is a round 2, right? So why not 0.3? Because while computing error, we'll weight each example xi by its weight dti, right? So in general, we can calculate the error on the classification error of your weight classifier on this weighted training set in this formula. So epsilon t equals half, subtracted half times the summation over all the m training examples, where each summand is the weight of the example times yi times h of xi. H of xi is 1 or minus 1. Positive 1 means that you classify as positive examples. Negative 1 means that you classify as negative example. Right? So here we want to give explanation why this is reasonable, right? Why this is correct, like. So our observation is here, right? So when we make a wrong prediction, that means y is not equal to h of x, right? Then what's the product of y times h of x? Is -1, right? So you make a wrong prediction. Then if your y, I mean the ground truth label, is positive, then your h of x must be negative, right? A -1. So their product is -1. If your ground truth label is negative, when you make a wrong prediction, that means your h of x must be positive, right? The product must be -1 as well. So this is like a very important observation, very convenient. We'll use that again in the future, right? So whenever we make a wrong prediction, that basically means our prediction times the ground truth label will always be -1. On the other hand, we'll make a correct prediction. No matter your ground truth label is positive or negative, the product of the ground truth and your prediction is always 1, right? So then, if you consider these two cases into this calculation, you can straightforwardly reduce the epsilon t here to be the summation of the weights for all the misclassified examples. It's very easy to show that. Okay. So I will leave it as an exercise for you guys to show this. Okay. So this guy actually is to calculate across all the mistakenly classified examples, what's the summation of those samples weights. Does it make sense? Okay. So now we'll proceed to the third round. We're going to still do the same thing, right? We want to increase the importance of the mistakes and then downweight the examples that H2 got correctly. So we can see that because these 3 examples are they are misclassified, right? So I'm going to increase this importance weight, right? And for the other examples, because they're correctly classified by H2, I'm going to downweight them. Okay. So this is the third round. This is after the second round. What's the weights for each example, right? And then suppose after the third round training, I got my third classifier H3, and of course H3 doesn't achieve 100% training accuracy as well, right? It still has some mistakes, right? And then if according to the formula, we calculate the weighted error, the error now is 0.14. Why is not 0.3? Again, because well, our rounds and rounds training procedure, every time we reweight the training example, and the error is the summation of the weights for the misclassified examples. So now, let us assume we're going to stop here. We'll only train 3 iterations, or we'll only train 3 rounds. We have collected 3 weak learners, H1, H2, and H3. You can see 2 vertical classifiers, 1 horizontal classifier, right? Now we want to seek a way to combine all 3 weak classifiers into a final one. So our idea is very straightforward. I just do a linear combination. I just do a linear combination of all the 3 classifiers. And of course, we need to consider how do we weight the prediction of each classifier denoted by alpha 1, alpha 2, and alpha 3, right? And here, alpha 1, alpha 2, alpha 3 can be treated as, or can be considered as the vote for each weak classifier, right? So the prediction of H1 is voted by alpha 1. H2 voted by alpha 2. H3 voted by alpha 3. And eventually, we're going to decide what's the total weight for the positive prediction and what's the total weight for negative prediction. And we choose the label who wins the votes, who wins the vote, right? Okay, that's the whole idea of ADA boosting. So you can see that the whole framework is as follows. So every time I'm going to start initially, I'm going to initially set a weight for every training example. Initially, it's equal weight for every training example. And then I repeatedly train a weight classifier. After I get a classifier, and I calculate the training error, right? And then I'll adjust the sample weight according to whether they are classified, they are correctly classified or incorrectly classified by my current classifier, right? I reweight them. And then on the reweighted training set, I run my weak learning algorithm again to get the second weight classifier. And then according to the performance of second weight classifier, I reweight every training example again. I just keep doing this until we have collected a set of weight classifiers. Then I do a linear combination of weight classifiers to derive our final classifier. And that's it. So any question regarding the general framework? Yeah, that's the detail we want to address in the next step. So here we're just to give the idea. But any idea? I mean, any question regarding the understanding of these general steps? Hope everyone feels this is intuitive, right? So now let us look at the outline, right? The outline of the boosting algorithm, right? So in general, suppose we're given M training examples, right? X1, Y1 to XM, YM. So here Xi's represent the instances of the feature vectors, and labels are represented by Yi, which is either +1 or -1, right? So we're gonna run the boosting algorithm for big T iterations, right? In each iteration, we're gonna construct a set of sample weights on every training example. And then we train our weak learning algorithm to find a weak hypothesis or classifier, which we denote by HT, right? And HT results in a weighted error epsilon T. Then using this epsilon T, we're gonna reweight the training examples in the next iteration. And based on reweighted training set, we find a next weak classifier. We just keep doing this, and then we'll have a collection of big T weak classifiers, and then we assemble them together into the final hypothesis. Usually people don't do that. Usually, like you said, just the maximum number of iterations. Usually they don't set a strong threshold that, okay, your epsilon T must be less than something. Because this is a weak classifier. Even you kind of reweight them again, it's very hard for you to get 0.01 epsilon T. It's very hard. Okay, any other question? A very good question. Okay, so now, what is difference between the boosting algorithms, right? The difference comes from how we're going to reweight the training examples in each iteration, and how do we assemble those big classifiers together. So different ideas of doing this will result in different boosting learning algorithm, right? And ADA boosting is a one representative instance of boosting algorithm, right? So we see that it leverages a particular rules to construct the sample weights according to epsilon T. And also you do some kind of linear combination, and they have a special choice of those votes, alpha 1 to alpha T, to combine those big classifiers. Okay, suppose we have now we talk about ADA boost, right? So here is how AdaBoost constructing DT, right? Suppose we have M training examples. So we denote at iteration T, the first example is weight by DT1. The second example is weight by DT2 until the mth example by DTM. Right? And at every round, the weak learner looks for hypothesis HT that emphasizes examples that have a higher DT, meaning that my weak learner will always try to correctly classify examples who has larger sample weight. Right? So for Ada boosting, right, at very first iteration, namely t equals to 1, we use the uniform distribution over all examples, meaning that D1I for every example I is simply set to 1 over M. M is total number training example, right? And after T iterations, what we have in hand is DT, meaning the set of weights for all the training examples, and the learned weak hypothesis HT. Okay? And we can also calculate the weighted error epsilon T, which is just the summation of all the weights of incorrectly classified examples by HT. Right? And in the next iteration, T plus 1, right? We want to find out a hypothesis so that examples that were incorrect in the previous round can now be correctly predicted by the new hypothesis. Right? That is, we want to increase the importance of misclassified examples and decrease the importance of the correctly predicted ones. So here is how Ada boosting update the weights. Right? So at round T plus 1, for every training example I, the new weight dt plus 1I is calculated in this way. So it multiplies the weight, its weight in the previous round, which is dti, by a factor. This factor is e to the power of alpha t or minus alpha t. Okay. So if you make a correct prediction, then you're going to multiply with e to minus alpha t. If you make a wrong prediction, you're going to multiply the previous weight by e to alpha t. So here alpha t is bigger than 0. E, the natural number, exponential. The previous weight is dti. So the weight at round t on example I. This is a notation, right? So dt plus 1I is okay. At round t plus 1, what's the weight for example I, right? So you can see that it just multiply the previous weight dti by this exponential factor. If you make a correct prediction, because alpha t is bigger than 0, so this one must be less than 1, right? So kind of downweight that example. If you make a wrong prediction, so e to the alpha t is bigger than 1, so you kind of promote the importance of the example, right? What? Let us finish the framework before we give the concrete example, right? Okay. Yeah. So these two cases can be summarized in one formula, such that you can write it as e to the power of minus alpha t times yi times ht alpha xi. Y is the true label, and ht xi is the prediction. So remember we discussed a moment ago, right? So if you make a wrong prediction, this product will be a -1, right? Minus become positive. You arrives at this factor, right? If you make correct prediction, so this guy is positive, right? +1. So it goes to e to minus alpha t. So these two cases can be summarized by one formula. So it's super convenient, right? In your implementation, right? And because alpha t is bigger than 0, so you can see that when you make a correct prediction, you kind of demote the example. If you make a wrong prediction, you're going to promote that example in terms of weight. And then the question is, how do we give alpha t, right? What's the setting for alpha t? In AdaBoost, alpha t is calculated as follows. So remember, epsilon t is the error, the weighted error of the weak classifier at iteration t, right? So you just calculate the ratio between 1 minus epsilon t over epsilon t, take a logarithm, take 0.5, this is your alpha t. And this one is positive. Why? Why is it positive? Yeah, error is less than 0.5, right? This is a weak classifier. It doesn't mean like it's bad, it's too bad, right? At least its error is less than 0.5, right? If it's less than 0.5, 1 minus epsilon t will be bigger than 0.5, right? So this ratio will always be bigger than 1. So then that means logarithm is bigger than 0, right? So alpha t is bigger than 0. This is how we choose alpha t in the AdaBoost. I mean, there could be other choices as well, but here we just talk about AdaBoost setting, and AdaBoost uses this, and it works well in practice. And eventually, those alpha t also serves as the vote to combine all the learned weight classifiers together. So you can see the alpha t is not only used to promote or demote examples, but also used for the vote for the weight classifiers. Okay, so this is basically the whole AdaBoosting algorithm details. So we'll revisit them again and discuss them more in our next lecture. So see you on next Tuesday.